The next gas law we're going to take a look at is Gay-Lussac's law. And Gay-Lussac's law says that pressure and temperature are directly proportional. And so if we keep the volume the same and increase the temperature, then that's going to increase the pressure, and vice versa. If we keep the volume the same and we increase the pressure, that should in turn increase the temperature. Same kind of relationship as it is between volume and temperature, but we're leaving the volume the same and talking about pressure. So Gay-Lussac's law says that the pressure and absolute temperature of a gas are directly related, and that's at a constant mass and a constant volume. So let's take a look at this gas law problem. It says that a gas's pressure is 765 torr at 23 degrees Celsius. At what temperature will the pressure be 560 torr? Remember, we need to change the Celsius to Kelvin. So what's given is pressure and temperature for one set of data, and pressure but needing to find the temperature for the second set. This is Gay-Lussac's law, so as pressure decreases, so is temperature. So here we have a pressure that is decreasing, so we should see a big decrease in the temperature as well. This, just like the last one, does not have to be written like this. It's not something you need to memorize this way. If it's easier, remember that the pressure of 1 over the temperature of 1 is equal to the pressure of 2 over the temperature of 2 because they are directly related. And we cross multiply and we end up with this reaction. So we plug those into this equation, we solve for T2, and we should get 217 Kelvin. You go ahead and subtract 273 from that to be able to turn it back into Celsius. It's negative 56 degrees Celsius. Again, easy math. Just remember to make sure that your temperature is in Kelvin, and that you make sure that you have the pressure in the same unit so that that's a consistency. So we're going to look at combined gas law, because we know that, as we back up, pressure times volume is a constant. We've looked at that. We have looked at volume and temperature being directly proportional as a constant, and pressure and temperature. So what would happen if we combine all three of those ideas? Well, this is what we would get: pressure, volume, and temperature. So we could look at a gas and look at three variables instead of just two at one time and put it into practice. So we can look at a gas under this set of conditions compared to this set of conditions. And again, in order to find the missing variable, you only have one missing variable. So we may have the pressure change. Maybe say the pressure goes up, the temperature decreases, and I have a volume that I want to know what would happen to this volume if I made these changes. And it's simple: cross multiply, divide, and solve for what you don't have. So there's no way to write it if you go ahead and do your cross multiplication. So a gas occupies 7.84 cubic centimeters at 71.8 kilopascals and 25 degrees Celsius. Find its volume at STP. And here we see STP pop back up. Now remember that that gives us a whole set of information. It's not that we just have three things. So let's see what that gives us. So given our volume 1, pressure 1, and temperature 1, that's all given right here, because it's at this pressure and it's at this temperature. Then we want to look at STP. So that's standard temperature and pressure. That leaves out volume. So I want to find volume. There's standard pressure and there's standard temperature. And notice I chose the one that was going to allow my pressures to be in the same unit, so I didn't have to do any extra converting. So I'm going to use the combined gas law. And like I said before, when I look at the combined gas law, I just think it's easiest if you do P1 V1 over T1 equals P2 V2 over T2. They're going to show you in this example where they go ahead and do the cross multiplication and plug in what they know and come up with what they need to find. In this situation, pressure goes up, the temperature goes down, and they expect the volume to go down. So let's look at the work. Plug it in. Solve for V, and you end up with 5.09 cubic centimeters. And I know I'm not spending a lot of time with the math part, but you all are in higher level math classes, and this is a simple algebra concept, so I'm sure that you can plug that into your calculator without any problems. So if we look back over here, our volume actually did decrease, which is what we expected to see here. So there's an example of the combined gas law.